Video 29 of the master course Quantum Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is induced electric moments and polarizabilities. So far we have assumed that the charge distribution, meaning the electrons and the nuclear charges, are not influenced by the applied external electric field or field gradient. This is, however, of course, not a realistic description. So in this chapter, we're going to look at the situation that the charge distribution will adjust itself to the presence of the external electric field. And of course, it will adjust itself in the way that the energy, the total energy of the system, is minimized. If the charge distribution changes, and one calls it is polarized, then of course the electric moments of the charge distribution also will change. And their value will then depend on the strength of the field. These field-dependent moments we can then write as the sum of two terms: the permanent moment, meaning the value which the moment has when there is no field present, and a correction term. A correction term which now depends on the field, and this correction term one calls the induced moment. Traditionally, one expresses this field dependence in terms of a power series expansion in components of the field to different powers. So the component of the electric dipole moment in the presence of the field is then the corresponding component of the permanent dipole moment. And here this power series expansion where we have increasing powers of the electric field. So here we have a linear term of the electric field. Here we have the product of two components of the electric field, meaning this term is quadratically dependent on the field and cubically and so forth. And how much the induced moment depends on the field is then expressed with these kind of expansion coefficients. Now, since we have electric dipole moment has three components and the field has three components, this proportionality constant in reality are 9 constants, which are the 9 components of what is called a second rank tensor. And this property is called the dipole-dipole polarizability, or typically just called the polarizability. In the next term, which is we have a quadratic depends on the field, we then have a proportionality constant, which in reality are 27 constants, which we combine all together in what is called a third rank tensor. And this property is called the first hyperpolarizability. And the next term we have 81 components of the second hyperpolarizability. Now all these polarizabilities, first hyperpolarizability, second hyperpolarizability, are in reality examples for response function as we have discussed them in the last chapter. So the polarizability, because it appears in the term linear in the field, is then a linear response function. The first hyperpolarizability is a quadratic response function. The second hyperpolarizability is a cubic response function, and so forth. Correspondingly, of course, the polarizability or components of the polarizabilities are first derivatives of the field-dependent dipole moments with respect to the components of the field, and the hyperpolarizabilities are then second derivatives, and the second hyperpolarizability are third derivatives. Now the question is now, what is the energy? And there we have to be a bit careful because we cannot just insert the expression here for our field-dependent dipole moment in the relation between the energy and the dipole moment in and the field. Rather than doing that, we have to look at an infinitesimal change in the energy when we change the external field infinitesimal. Here's just a normal relation between the energy of a dipole moment in the presence of the field. But now we infinitesimally change the field and we have a field-dependent dipole moment. If we then want to have the value of the energy for a given value of the field, we just have to integrate on both sides of the equation. So on the left side, we get the change in the energy from the field free energy to the energy in the presence of the field. And then we have to integrate here over the field-dependent dipole moment times an infinitesimal change in the electric field. This integral in reality, of course, is a product of three integrals because this is a vector here, so we have to integrate over the x, y, and z component of the electric field. Now, this kind of integral actually is a line integral over a vector field here. Dipole moment is a vector, and it depends on another vector, so it's a vector field. And the space in which we integrate is actually defined by the components of the electric field. Now, you might remember from mathematics that these kind of line integrals, I mean, you normally see the line integrals, of course, in three-dimensional space. So you would have x, y, z as the coordinates. Here we have sort of three components of the electric field as the coordinates. But otherwise the same. So a line integral is independent of the path when the vector function, which is our dipole moment here, is the gradient of a scalar single-valued field with continuous derivatives. And remember that we defined, or we could express the electric dipole moment as a derivative of the energy with respect to components of the external field. And the energy obviously is a single valued field, and it has continuous derivatives. So we can choose the path along which we want to integrate freely because the integral is independent of the path. Now, of course, the easiest path is to choose as that we integrate first along, just change one of the components of the electric field, then for example, x, and keep y and z constant, which in the beginning, of course, 0. Then we change the y component from 0 to its final value, and in the last step, we change then only the z component from 0 to its final value. And that's what we're going to do now. So as I said, we integrate 3 steps. We integrate from a 0 field to a field which has the final value for its x component, but the other two are 0. Then from there to where also the y component has its final value, and finally to the z component also having its final value. Doing that, and you're going to do that in one of the exercises, we arrive at this expression for the energy in the presence of the external field, being the field-free energy, and then the contribution, which we already knew from the permanent dipole moment and the field. But now we get 3 extra contributions here from the polarizability, the first hyperpolarizability, and the second hyperpolarizability. And you can see now the term with the polarizability has now the field or 2 components, the field quadratic, meaning we have the polarizability multiplied with 2 components of field, the first hyperpolarizability multiplied with 3 components of the field, and so forth. Now, if you know what the dipole moment of a molecule is, and its polarizability, first hyperpolarizability, second hyperpolarizability, then we can calculate the change in the energy of that molecule for an arbitrary value of the electric field just by this equation. We just have to insert whatever value of the electric field components we want to consider, and we can calculate what the energy is. Now, in previous sections, we talked about that this moment expansion of, for example, the electrostatic potential of a molecule is very useful in calculating interactions between molecules, changes in the energy due to intermolecular interactions. And we looked at dipole-dipole interactions and similar contributions. Now here, this expression fulfills the same role, but now we have polarizabilities in there, and that gives actually rise to a new part of a new contribution to the interaction energy, which is called the induction energy. So that's the induction energy contribution to intermolecular interaction, which comes, for example, if I have a molecule which has a dipole moment, which then will induce a dipole moment in the other molecule, and therefore there's a term where we have an interaction between the dipole moment of one molecule and the polarizability of the other molecules. Another application of this expansion of the energy is similar as we did it in the expansion of the energy in terms of moments. We can use it to derive expressions for the polarizability or components of the polarizability, first hyperpolarizability and so forth, as derivatives of the energy with respect to obviously now two components of the field. So we can sort of collect all those expressions for the polarizabilities and hyperpolarizability as derivatives, and we can define them A as derivatives of a field-dependent dipole moment or component of the field-dependent dipole moment, where the polarizability as a linear response function corresponds to a first derivative, and the first hyperpolarizability as a quadratic response function corresponds to a second derivative, and so forth. Simultaneously, we can also define them as derivatives of the field-dependent energy here. And there now the polarizability is equal to minus a second derivative of the energy, or derivative with respect to two components of the electric field. Which is the reason why sometimes polarizabilities are also called second order properties, because it corresponds to a second derivative for the energy. And first hyperpolarizabilities are then called third order properties because they correspond to the third derivative of the energy with respect to three components of the electric field. Now, as I said already, the polarizability is what is called a second rank tensor. The hyperpolarizability is third rank tensor. So there are 9, 27, 81 components. And one can, for those tensors, define isotropic values, which are isotropic averages and correspondingly anisotropies. For the polarizability, the isotropic value is 1 over 3 times the sum of the diagonal elements, meaning the sum of the xx plus yy plus zz components of the polarizability tensor. That's called the isotropic polarizability. And the anisotropy is defined in this way as the square root of the sum of different components of the polarizability, written like here. Now for the first hyperpolarizability, there are two different isotropic values in the literature. One is the parallel isotropic value and one is the perpendicular isotropic value as defined here. And it's the sum of different components of the first hyperpolarizability. The Z component here is not just some arbitrary value, but the Z has to be the molecular axis which is parallel to the electric dipole moment. So the electric dipole moment is pointing along the Z-axis. Also for the second hyperpolarizability, there are two isotropic averages around. Again, a parallel or a perpendicular, and sometimes you will find that this parallel is also just written with a bar above it, like for the polarizability. And these are the two definitions how you can calculate them. In this presentation, I know I have only talked about dipole moments, induced dipole moment, dipole polarizability, but you can do precisely the same expansion also for the quadrupole moment. You get an induced quadrupole moment. So you can look at a situation where you have electric field gradient present, which will change then the quadrupole moment, actually also will change the dipole moment. So you will get polarizabilities, which are quadrupole polarizabilities, and you will also get dipole quadrupole mixed polarizabilities, as I've mentioned them in the book.